All right, everyone. Let's start with part 2 of the lecture 7, which is again more review problems for proofs. All right, so there's 2 questions here, and I would pause the video right now and try to solve it on your own. I think each of the problem is going to take between 2 to 5 minutes. Okay, I'm going to start solving the first one. Okay, you might have seen this before. So what I'm going to do is just a quick review, or in another way, it's a sketch of the proof techniques. And then next page will have more detailed more proof details. Okay, all right. So here, the first one, to prove that if n squared is even, so is n. Then what we are going to do as part of the sketch of the proof is we're going to prove by contrapositive statement. Okay, so what is a contrapositive statement? Recall P implies Q is logical equivalent to not Q implies not P. All right, so in this case, the contrapositive statement is n is odd implies n squared is odd. Okay, again, I'm only going to write the sketch of the proof. Okay, so first of all, the hypothesis is n is odd. This means n can be, by definition of odd integer, n can be expressed by 2k plus 1 for some k that's integer. Okay, next thing we're going to do is to use substitution, where n squared is now equal to 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1. Okay, I'm going to do factorization. Now I get factor 2 out. And then the last step I need to do is to use the closure property to show that 2k squared plus 2k is an integer. Okay. Of course, when you're actually solving this in detail, this is you should not write just a sketch. What you should follow is a detailed proof that is shown in blue here. Okay. But the highlight of this problem, again, is proof by contrapositive statement. And then you use the definition of an integer being odd. You're going to use substitution and then closure property of integers. All right, let's look at the second problem. Prove that every perfect square is of form 4k or 4k plus 1. Okay, so in this case, again, I'm going to just sketch the proof. I'm going to prove by case. And in this case, I have 2 cases, and I'm going to use n to represent integer. Okay, so for case 1, this is when n is even, and of course, case 2 is when n is odd. Okay, so when n is even, by definition of even, n is equal to 2p. Then we have n squared by substitution is 4p squared, right? And then if we set k is equal to p squared, or by the closure property of the integer, k is also integer. K is integer. So now n is in the form of 4k. Now the second case is when n is odd, so n is equal to pk plus 1. Then by substitution, n squared is equal to 2p plus 1 squared, which is equal to 4p squared plus 4p plus 1. I factoring out 2, so it's 2 times 2p squared plus 2p plus 1. So again, what we can do is we can set k is equal to 2p squared plus 2p. Of course, the last step is we want to show that k is integer. Same thing here. We want to show that k is integer. Of course, this is by closure property of integer. Okay, so this is just a sketch of the proof. And then, of course, here in blue is the detail of the proof. Okay, so again, in exams, please write out all the details. right? By the definition of even number, by substitution, by closure property under multiplication. So those are some of those details that should be included in the actual solution of the problem. Okay. Next one. Prove that given 7 integers, there's 4 of which the sum of square of the integer is divisible by 4. Okay. So we actually have seen this problem before. So what I'm going to provide is a sketch. Again, when you see this problem, the first thing come to my mind is we are going to apply the pigeonhole principle. And then to apply pigeonhole principle, I need to solve for number of object, number of container, and number of items or object that falls into the same container. So in this case, I have mn plus 1 is equal to 7. That's total number of integers. And it said that there will be 4 of which that satisfy certain property. So that means at least 4 of them falls into the same container. So now using this 1 and 2, use 1 and 2 to solve for n, right? So we get n is equal to 2. So that means we're going to have 2 containers. So the question is, how do we design this container? Okay. So version number 1, which I think I'm going to leave it as take home, is for you to think that what might be a good container design based on the property that is divisible by 4. So one thing come to my mind is to say that, okay, I'm going to look at essentially the property of a number mod 4 is either equal to 0, 1, 2, or 3. And then maybe my 2 container can be based on the remainder of a number mod 4. So maybe I will put, if their remainder is 0 or 2 in the first container, if the remainder is 1 or 3 in the second container. You can still prove this, but this is going to be quite complicated, but I think it's still doable and it will be a take-home exercise. But it turns out for this particular problem that I don't have to focus on the property divisible by 4, but I can think about an integer to be divisible by 2. So what does that mean? That means my container is going to be 2 container again, but I'm going to study n mod 2, which has a remainder of 0 or 1. Okay, so the first container is if it's even number, second container if it's odd number. Okay, it turns out this design will be sufficient, design of containers will be sufficient for this problem. Okay, so what do we do now? What we assume there's 2 integers that's going to fall into the first container or the second container. So I have 2 cases. Case number 1 is when both number or 4 numbers that falls into the first container. So let's say those 4 numbers x1 is equal to 2k1, x2 is equal to 2k2, x3 is equal to 2k3, and x4 is equal to 2k4. Okay. And in this case, x1 squared plus x2 squared plus x3 squared plus x4 squared through some multiplication is equal to 4 times k1 squared plus k2 squared plus k3 squared plus k4 squared. Okay? And you can show, again, by closure property that this sum is divisible by 4. Second case, case number 2, is when all numbers are odd integers. So x1 is equal to 2k1 plus 1, x2 is equal to 2k2 plus 1, and same thing with x3 and x4. Again, if I take the sum of them together, and through some factorization, you are going to get 4 times k1 squared plus k2 squared plus k3 squared, k3 squared plus k4 squared plus 1. Okay. Again, by closure property, this sum is also divisible by 4. Okay. So this is just a sketch. The main idea is that it turns out I can design a simpler container here just based on whether integer is even or odd. Of course, this is actually the detail of the proof. You need to, kind of describe, again, using definition of even or odd integer and using substitution and using closure properties of integers. All right. Next one is to say, prove that for all real number x, if it's bigger than 0, then 1 over this real number is also bigger than 0. Again, what is my sketch of my proof? Okay. Here, I want to prove by contradiction. If I want to prove by contradiction, I would like to suppose there exists essentially a counterexample. What is this counterexample? That is a real number x that is bigger than 0, such that 1 over x is smaller or equal to 0. Okay. And you want to show that this counterexample does not exist. Okay. All right. So let's say, assume the counterexample does exist. Then we have the property x, 1 over x, x is bigger than 0, but 1 over x smaller or equal to 0. Because x is bigger than 0, I can multiply both by x. So if I multiply both by x, I have x times 1 over x smaller or equal to x times 0. Because when you multiply a positive number on both sides of an inequality, the direction of the inequality does not change. So now I can solve it. On the left-hand side is actually 1. On the right-hand side is 0. So I arrive at the conclusion that 1 is smaller or equal to 0, which leads to a contradiction. This is not true, right? So that means when I assume there's a counterexample that leads to a contradiction, that means the original statement is true, meaning that there's no counterexample. Again, this is a sketch. The blue text here is the actual detailed proof. And I would encourage you to go over it carefully. Okay. Now, next one, we're going to see some example using proof by induction. Okay. So it's given a recursive formula, and we want to prove that it is equivalent to a closed form formula for a sequence. Okay. So again, let's go back to the fourth step. What is a problem statement? What is base case? What is induction hypothesis? And what is induction step? And after induction step, we can arrive at our conclusion. So problem statement is that, well, it says A1 is equal to 5 and AK is equal to AK minus 1 plus K plus 4, and PK is equal to K times K plus 9 over 2. And we want to show, well, as part of the statement is AK is equal to PK. Okay. The base case, is we want to show that A1 is equal to P1. Okay. How do we show that? A1 is equal to 5. And P1, we can substitute into the formula, which is 1 times 10 over 2. Okay, so it's 1 times 1 plus 9, which is 10, and this is 5. Okay, so we know that A1 is equal to P1 for the base case. Now, induction hypothesis is we want to assume that the statement is true for n minus 1. So I want to show an minus 1 is equal to Pn minus 1. Okay. So what is Pn minus 1? Pn minus 1 is n minus 1 times n minus 1 plus 9, which is n plus 8 over 2. Okay. Of course, I have simplified a few steps. Now, for induction statement, I want to show that AN is equal to PN, okay? So what does this mean? This means I'm going to, of course, using induction hypothesis, okay? In this case, I'm going to say AN by the recursive formula is equal to AN minus 1 plus N plus 4. I'm going to substitute AN minus 1 in here, okay? So remember, AN minus 1 is equal to N minus 1, N plus times N plus 8 over 2 plus N plus 4. And I'm going to go through a bunch of algebra. So the top is equal to 2 times N squared plus 7N minus 8, and then plus 2N plus 8. Again, this is just some basic algebra, and I'm going to simplify it. What I get is going to be N squared plus 9N. The 8 and minus 8 cancel out. And I do some factorization that leads to N times N plus 9 over 2, which is equal to P of N, okay? So once I showed AN is equal to P of N by induction, this is true for all N, and we arrive at our final conclusion. So again, this is my sketch. If I want to go through the detail of the proof, the blue here shows the details. Okay. Let's do one more problem surrounding induction. Okay. So prove that for each integer n bigger than 1, bigger or equal to 1, n to the power 5 minus n is divisible by 5. Of course, here we provide a little bit hint of how to expand n minus 1 to the power 5. All right. So again, as part of my sketch, I'm going to have to talk about what is my problem statement, what is my base case, what is my induction hypothesis, and what is my induction step. Okay. In here, for simplicity, I'm going to name my statement to be P of N. So the statement for P of N is to say that for n bigger or equal to 1, 5, n to the power 5 minus n is divisible by 5, or 5 divide this number, or alternatively, I can say n to the power 5 minus n is equal to 5 times, let's say, k for some integer k, okay? So this is the same as saying it's divisible by 5. Now, the base case, we want to show the statement P of 1 is true. What does that mean? That means I need to say that if I compute 1 to the power 5 minus 1, which is 0, this is equal to 5 times 0. Again, this means that 5 can divide can divide 0 to the power 5 minus 0. Okay. Of course, if you want to do, oh, actually, never mind. Sorry. Yes, so your base case here is starting from the first integer that is non-zero, right? So you have to start with this. So of course, the base case is 1. All right. So now what is my induction hypothesis? A hypothesis is going to say, assume P of n minus 1 is true. What does this mean? This means n minus 1 to the power 5 minus n minus 1 is going to be divisible by 5. So we are going to say this is equal to 5q for some integer q, okay? And now for the induction step, we want to show P of n is true, okay? Right, so now we have to use induction hypothesis. Let's go back to induction hypothesis. Based on induction hypothesis, n minus 1 to the power 5 minus n minus 1, if I use this equation provided by part of the problem, I can expand n minus 1 to the power 5. So what I get, n minus 1 to the power 5 is going to be n to the power 5 minus 5n4 plus 10n3 minus 10n squared plus 5n minus 1. And I'm going to minus n plus 1, right, which is the second term. Of course, 1 cancel out together, And what I get here is I do some rearrangement on the right-hand side, m to the 5 minus n minus 5n4 minus 10n3 plus 10n2 minus 5n. Okay, so because what we're looking for is really the expression of this, by induction hypothesis, we kind of already there. So if I do some rearrangement, I have n to the power 5 minus n. You know, of course, this thing here by induction hypothesis, this is equal to 5 of q. So do some rearrangement, I will get n to the 5 minus n is equal to 5q plus this term, okay? And again, I'm going to do some factorization. I'm going to get m5 minus n is equal to 5 times q plus n4 minus 2n3 plus 2n minus 1, okay? So, no, sorry, minus n. Did I get it right? No, 3, this is square. All right. So of course, by closure property of integer, this is an integer here, and then we're down because we can express 5n, but n to the power 5 minus n by 5 times some integer. Okay. Of course, this is just a sketch. This is a detailed proof, and I will encourage you to read it and compare it against your own solution. Okay. All right, we're moving on to the last problem. Again, I'm going to talk about the sketch of this proof. Okay, this is a slightly tricky problem because, again, we want to use pigeonhole principle, but the design of the container is a little bit tricky, okay? So it says if there's 26 distinct integer that is sampled randomly from 1 to 50, then you want to say at least one pair of those numbers is consecutive. So when you say one pair, okay, one pair, that means what? That m plus 1 is equal to 2. So m is equal to 1. And then we have 26 objects. So m plus 1 is equal to 26. Then if I solve for n is equal to 25. So you need to design 25 containers. Okay. And then there's one property from this problem statement we haven't used, is that we want those integers that falls into the same container to be consecutive. All right. So what can we do? Okay. So it turns out I can design, because I'm drawing numbers from 1 to 50. So I'm going to design containers so that each container has a pair of consecutive integers. So what I end up having is I'm going to design, you know, again, I'm going to design 25 containers. But the first container is if the number is 1 or 2. Second container is the number falls into it is 3 or 4. The third container is 5 or 6. The last one is 49 or 50. Okay. So what's happened, there is 25 containers and I have 26 integers. So at least 2 of them is going to fall into the same container. But if 2 of them falls into the same container and they are distinct, it means that they have to be consecutive because that is by design. Okay. So this is a high level overview of the proof of this problem. All right. So if you have any questions solving these problems, please come to the office hours. Okay. And good luck and have a good week.